Hi friends, today our topic is again dwdm. Fiber is a thin strand of glass or plastic that serves as the dwdm transmission media. Fiber is a dwdm transmission media. For single mode, the loss is 0.275 dB per kilometer and for 1550 nanometer and 5 dB per kilometer for 1310 nanometer sources. Multiplexing is the process of combining two or more signals together based in space-time or wavelength division. Multiplexing is the process of combining two or more signals together based in the process of space-time or wavelength division. Different signals with specific wavelengths are multiplexed into a fiber for transmission. Earlier, HDS technology was having less capacity, so DWDM introduced because of HDS technology was having very less fiber capacity. DWDM is a transmission technology by which we can transmit demultiplex different wavelengths on a single fiber by which we can utilize maximum bandwidth by a fiber. DWDM is a transmission technology by which we can transmit, demultiplex different wavelengths on a single fiber by which we can utilize maximum bandwidth by a fiber. DWDM combines multiple optical signals so they can amplify on a group and transported over a single fiber to increase capacity. Here O band is original 1260 to 1360 nanometer, E band extended 1360 to 1460 nanometer, S band short wavelength 1460 to 1530 nanometer, L band C band conventional or LVM window 1530 to 1565 nanometer, L band long wavelength 1565 to 1625 nanometer, U band ultra long wavelength 1625 to 1675 nanometer. O band original 1260 to 1360, E band extended 1360 to 1460, S band short wavelength 1460 to 1530 nanometer, C band conventional or Arabian window 1530 to 1565 nanometer, L band long wavelength 1565 to 1625 nanometer, U band ultra long wavelength 1625 to 1675 nanometer. O and E around 1300 nanometer have much more losses. This region has zero dispersion. 1300 nanometer region has the advantage of zero dispersion but having much more losses while we compare it 1550 nanometer window. Middle windows S and C are most widely used, but in case of DWDM, C and L are most widely used. It does have some dispersion, but with loss 0.275 dB per kilometer, so we use dispersion capacitor to remove dispersion. The 1550 nanometer window. Channel spacing is minimum frequency separation between two different multiplex signals. Channel spacing is minimum frequency separation between two different multiplexed signals. 1980 two channels wideband WDM 1310 and 1550 nanometer window channels. Early 1990 2 to 8 channels in 1550 nanometer, that is second generation WDM. Channel spacing was 3.2 nanometer. In mid 1990 16 to 40 channels in 1550 nanometer DWDM, channel spacing 0.8 to 1.6 nanometer. In late 1990s, 64 to 160 channels in 1550 nanometer window. This is next generation DWDM. Channel spacing is 0.2 to 0.4 nanometer. A basic DWDM system contains below main components. Some main components: DWDM, OTM, in OLA, an intermediate optical terminal for pass-through dual terminal, uh, WTM terminal multiplexer, demultiplexer, OTM, and OC for remote site management. First is dwdm OTM for multiplexing. Second is demultiplexer, that is also dwdm OTM. It means OTM performs two functions: multiplexing and demultiplexing. We use OLA for repeating amplification of the signal, and there is pass through for pass through channels after some distances 500 km or 900 km, 500 km. This is DT sat DWM terminal intermediate optical terminal, dual terminal we can say, and there is OC channels also for remote site management. DWDM. DWD is a transmission technology by which we can transmit, multiplex, or demultiplex different wavelengths on a single fiber, by which we can utilize maximum bandwidth via fiber. O band 1260 to 1360, E band 16 1360 to 1460, S band 1460 1530, C band 1530 1565, L band 1565 1625, U band 1625 to 1675 nanometer. Thank you.